before that, I want to make a comment because this was a discussion during tutoring sessions and in this area after the talks. So there was this question about admissibility and what Harishchandra proved and what other people proved. So Harishchandra, in his proof of admissibility, assumed that representation comes from representation of the group. There is a paper of Lepovsky which proves Harishchandra's subquotient theorem without this assumption, much later. But there he says this is exactly Harishchandra's proof, except that he replaces some lemma by some other lemma. So essentially, by slight modification of Harishchandra's original argument, one can drop this, and then for, say, GK modules, as I define it, if they're irreducible, one can use this to prove subquotient theorem of Harishchandra. So those are representations in Dragan Helder series of a principal series, so they're admissible. And so the attribution, I think, is quite clear, who's 99% of the result is. Okay, so let me discuss this geometric classification. So what we know by now that we have this category of, say, coherent B lambda K modules and the Harishchandra sheaves. And we claim that they are holonomic. And I sketched the proof of holonomicity, and also during tutoring session, I sketched the proof that K acts in finitely many orbits on the flag variety. So this is basically modular little technical details is covered. So now I want to explain how you can describe irreducible objects. And this, I think, is appropriate to do here because once you see this proof, you will always remember how it works. This is one of the things which is so beautiful and simple that it's worth discussing. First of all, so let's assume that I kind of sketched the idea why holonomic modules are of finite length. So they have finite composition series such as subquotients are irreducible. So irreducible, if we understand irreducible object, we know a lot about holonomic modules. So let's assume that V is an irreducible Harishchandra sheaf. So this implies, if you think about this, that its support, what is a support, say, of a D module? This is the complement of the maximal open set on which this D module is zero, when we restrict it. So we have a definition of support. And if V is irreducible, then an easy exercise is to show that support of V is an irreducible subvariety in X. On the other hand, our Harish-Chandra sheaves are K equivariant, so this support is K invariant, and since we have finitely many orbits, it's a union of finitely many some subset of this finitely many orbits. But irreducibility, again, this is an exercise to show that its irreducibility implies that this is closure of one orbit. Basically, you look at these finitely many orbits, you pick an orbit of maximal dimension, and then it has to be dense in the support. The support is its closure. Otherwise, this would contradict irreducibility. So, to our V, we attach the first invariant. So this is Q, which is a K orbit, such that closure of Q is support of Q. So what else we need to describe V precisely? So this is the second step. The first information is the this orbit attached to the K orbit. Now let's look at the picture we have. We have our orbit Q, and we have its closure. There is, I don't know how to draw the picture, but there is something in the boundary of Q, which we do not understand at all. Thank you. So, what do we do? This is one advantage of D modules. They're sheaves, so we can do various stupid things we cannot do with representations. And we just drill a hole here, we throw away the boundary. So we take in the flag variety, we take a set, say, x prime, which is x minus the boundary of Q. So this is an open subvariety of x. And first remark is that if I have an irreducible D module, then its restriction to an open set is either 0 or it stays irreducible. And here, what is important is that we are dealing with a category of quasi-coherent D lambda modules, and there is a simple lemma of Grothendieck's which says that if I have an open set, I have some quasi-coherent OX module, I have an open set, and I look at the restriction and take a submodule that this submodule extends. And this works over for the lambda module, the same proof. And this tells you if you restrict and you get something reducible, then the original D module is reducible. So the conclusion is that our V restricted on X prime is irreducible. And of course it's holonomic. Because, as I mentioned last time, holonomicity is local property. So now we have a different situation. We have X prime, and our orbit Q is now a closed subvariety of X prime. So now there is a construction of direct image of in the category of D modules, which is quite subtle in general for arbitrary morphisms of varieties, but in this case, it's very simple. If you take a D module on Q, then of course you know how to differentiate along Q. You don't know how to differentiate in normal this direction, and then you take just the formal sum of the stuff you get by differentiation. This is, if you remember the example I mentioned last time, if you take a point in a complex plane, this is a D module over a point. Just say, if I take C here, because differential operators are constants and they obviously this, and then you consider derivatives of delta function. These are just copies of this module where E from so one point to the higher derivatives you go by applying formally the differentiation. And you can do this in general. If you have a smooth subvariety, you do it locally by describing this subvariety with a bunch of equations, and then you can glue this together and this construction works. Does this make sense? I mean, in some kind of intuitive sense. This is like SL2 Verma modules, which similar calculation here. So this D module, which you get as a direct image, say I over plus, this will denote I, is the, say IQ is the inclusion of Q into X, and there is the functor IQ plus, which goes from the category of D modules on Q in the category of D modules on, in this case, X prime. And we can do this in twisted case, the construction is local. The point is that this functor is an equivalence of categories between the category of D modules on Q and the category of D modules on X prime supported in Q. So this is so called Kashiwara's equivalence. For example, this delta distribution construction in the case of C constructs an irreducible D module supported at origin in complex plane, and the theorem says that the category of vector spaces is equivalent to the category of D modules with the support in this point. So basically, this subcategory, category of D modules is semi-simple and irreducible objects are just these D module constructed using derivatives of other functions. So this is the result we are going to use. As I said, what we concluded that f restricted to x prime is irreducible and holonomic. Therefore, this v on x prime is, say, okay, let me call this j, otherwise I will mess up all my further notation. Okay, and here's x prime. Is this j, say, q plus the direct image and of this morphism of some tau, which is a D module on Q. With, of course, the twist on the big variety induces also twists on the orbits. Now, another thing which is quite easy to show, if you write down locally this construction of direct image and Cauchy-Weyer's equivalence, you can see what happens with the characteristic variety, and you see that this equivalence also preserves holonomicity. So, this tau is also holonomic. Now, since it's holonomic, its characteristic variety has to be of the same dimension as the orbit. But since the group K acts, so this is an equivariant K module, then tau will be equivariant D module on the orbit. So basically K react on the orbit and the D module, and a characteristic variety should look everywhere the same. Now, if you look at the definition of holonomicity, if you will have at some point something in a conormal, in a cotangent space in characteristic variety, then this would be at all the points. And your dimension of characteristic variety should be bigger than dimension of the space of zero sections. So it will be bigger than Q. So the conclusion of this discussion is the characteristic variety of tau is the zero section in cotangent space. And then there is a little lemma which says that if you have a D module, which is coherent, and its characteristic variety is a zero section on the zero section cotangent space, that this D module is coherent as OX module, and then it is locally OX free, and this is what Bernstein calls a connection, because this is really, in a classical language, is a sheaf of sections of a vector bundle, and the connection on it, which is given by D module structure, is integral. So this is the connection. And since this connection is has to be reducible as a D module, as I said, it's coherent OX module, and it is K equivariant. So if you put all of this together, you see that there exists this tau is a sheaf of sections of homogeneous, K-homogeneous bundle on Q, which is given by a representation of the stabilizer, and it has to be reducible. So the representation of the stabilizer, and the stabilizer, if you want, is essentially the quotient of K by the corresponding Borel at that point X. So if this is my point X in the orbit, then the stabilizer in K is essentially this. Say K sits inside G. Yeah.
So when you explain, you are removing the boundary of Q from that, right?
Yeah.
So that, then we don't know whether it's going to be stable at the K.
No. The boundary is union of orbits. Just by, I mean, by very definition.
Okay.
Yes, I mean this is like all of this works. That
the boundary would be something like it corresponds to some sort of flat value of smaller dimension.
I mean, boundary. This closure of Q will be highly singular. This is the reason why, say, Kazhdan-Lushik polynomials are so complicated, because they are determined exactly by the geometry of the boundary. But since your Q is invariant at the K action, so the closure of Q is also invariant, and then since the risky topology is nice, if you throw away the open orbit, what is left in the closure are orbits of lower dimension. And so if I throw them away, our Q stays closed in X prime. Agree?
So it would be almost like the boundary of Q would be some sort of a Schubert-Sill boundary. And that kind of
Yeah. In the case if K is N in the highest weight situation, this is exactly true. Here the group K is different, so things are different, but formally they're the same. Agree? Any other questions? Okay. So this gives me this Q and tau when tau is K equivariant connection on Q, which is, say, reducible. And also, I mean, if we follow the twists carefully, we can see that differential of the representation of the stabilizer is given by restriction of copies of lambda plus rho to the Lie algebra. So let me point out what this means. The Borel, in this case, its Lie algebra is, of course, a sum of some Cartan subalgebra and corresponding Lie algebra n of x, and we can use the specialization of lambda plus rho in this case and extend it trivially on n of x, and then this gives me a linear form on the Borel. We restrict it to the Lie algebra of this, and so the representation of the stabilizer have to have the differential, which is some of these guys. This is exactly the twisting condition. And now if you think about this condition will force the number of such representations which have these properties finite, so there is a finite number of irreducible connections for a given lambda, which can appear as a second variable in this pair. And let's call this geometric data. For example, in a case of category, corresponding category for highest weight modules, as I said, we would replace k by n. In this case, the orbits, as you point, in the case of Bruja cells, if you look at these stabilizers, they will clearly, there will be n. So this this condition will be kind of void, and you will have only on each Bruja cell, you will have only one connection, and this will be the structure sheaf of that Bruja cell, and with the induced action of differential operators. And therefore, in this case, the number of these geometric data will be exactly the same as the number of orbits, as the number of Bruja cells, but should be the case, as you see in a moment. But say in SL2, if you look at a picture, then we said last time there are 3 orbits. The stabilizers at these 2 points are Borels, and therefore, if you go through this analysis, that you can choose a torus in the Borel, which is just Kc in this case. It's just K in this case. So lambda plus rho will tell us, first of all, the lambda plus rho has to be a weight on the Cartan. And the second thing, it will completely determine the representation of the stabilizer. So here you will have integrality condition. So then on one hand, and also orbit for each integral lambda will give you exactly one D module. Here, the stabilizer of an arbitrary point is plus minus identity matrix. So these conditions will give me nothing, but there will be two possible representations of the stabilizer. Trivial and the sign, and this corresponds to the fact, as you will see in a moment, that there are two principal series in SL2, as we have seen from the calculations of these representations. Okay, but how to get to our irreducibles? If I have this set of geometric data, I could do the following. Now I will take I of Q is the map from the orbit Q into fly variety X, and then I can do the direct image from differential operators on Q to differential operators on X. Now we have to use, say, the most difficult result in D modules in the set, which requires really a bit tricky proof, which was given by Bernstein in his original paper on D modules, that this functor always preserves monomicity. I mean, this functor is composition of two functors. Say Q, first I can embed Q by JQ in X prime, and then I can say use embedding K of X prime into X. So this is an open embedding. So here, the direct image of the this is the, say, IQ. The direct image behaves well with respect to compositions, and by this is controlled by Kashiwara. The hard part is to show that the direct image from an open subset to all variety X, which is just the standard sheaf theoretic direct image, preserves holonomicity. I mean, remember in our situation that, say, for O module, this is, things go wrong. If you take something, say, coherent O module on X prime and push it forward, you will get quasi-coherent. But the fact that you have the action of D modules forces, for example, this sheaf theoretic direct image maps something of finite length into finite length. This is kind of tricky. But if you know this, then you observe that you have the following adjointness relation. Our if I look at K plus, so it says B modules on X prime into B modules on X. And as I said, K plus is a sheaf theoretic direct image, and we have the adjointness that home in the category of D modules now I am just improvising the notation, not to make it too complicated. So this is just restriction of my sheaf of x prime, say some u restricted to open set x prime into say w. This is the same as on d of x of u into directed. So here in this step, I mean, this guy maps irreducibles to irreducibles, but when we apply k plus this, which is just the sheaf, yeah.
Those D modules, I mean, the script D modules and this classical Milicic, they are different or are they the same structures?
I mean, this is just, you're right, they are the same, but the base space is smaller. So you take just your sheaf of differential operators and restrict it to an open subset. And so for any smaller open subset, these are the same differential operators in the big thing.
These are something like a local pictures.
Yeah. So now,
I had one more question.
yes.
This, I mean, the adjoint counter over here, that would be almost like a forgetful counter in this right? We are going from the D modules and x prime, which is going to be a subspace of x, and so the adjoint.
I mean, here I have a restriction, and the restriction is adjoint to the.
So that's the push forward.
Yes, yes, yes.
We move from plus to star.
Yeah, okay. I mean, I wanted to stress that this is same as shift here. Yeah, no, it's right. So now, think about what this means. If my u is, I mean, irreducible, but not supported in the boundary. So supporting this x prime, then this stays irreducible. So if I take this irreducible thing and replace w with this, then here I have one canonical morphism, and this will give me the map from my irreducible into this. And if you think about this for a moment, you will see that this implies that there is unique irreducible sub in this direct image. Because you see, if you will have two and you restrict them, then I mean, between them, if they're not isomorphic, then this would be 0, and then this would contradict this. So there, if you think about this for a moment, you see that this k lower plus of w has a unique irreducible sub-object, and basically, if I put this guy here, this tells me that my u, which I restricted to x prime, sits in, so this is the conclusion which follows from this adjointness. And this is unique, irreducible sum. So if you put these things together, then I can take my second thing and IQ plus of tau, which I will call is a Harshchandra sheaf. I'll call it standard Harshchandra sheaf. And it has unique, irreducible sum. Which we denote by L, Q, tau. In the category of Harshchandra sheaves. And this is irreducible Harshchandra sheaf attached to the data to Q tau. And the theorem is, and essentially, if you think about this, you will see that this is what we proved in this discussion, modulo some dots on i's, that all irreducible Harshchandra sheaves are isomorphic to LQ tau for Q tau. And this is the first statement, and the second statement is LQ tau is isomorphic to LQ tau prime if and only if tau is isomorphic to tau prime. So basically, geometric data parameterizes reducible Harshchandra sheaves. And from this discussion before, this tells us that for a given lambda, there are finitely many irreducible Harshchandra sheaves. Or if you are in anti-dominant situation and use equivalence of categories, this tells you that the number of irreducible Harshchandra modules for a given infinitesimal character is finite. So we see that for a given infinitesimal character, we have finitely many irreducible Harshchandra modules, and we got it just using this localization technique. For example, again, let me look at the SL2 picture. As I discussed a moment ago, there are three orbits in a flag of K in a flag variety of SL2. Because K is C star and it acts 5 by right by multiplication by c squared. So there are 2 points, and there is open orbit. If I look at these 2 points, the compatibility condition will tell me that there are Harshchandra sheaves for integral lambda, and lambda is a weight, 1 for each of those at the points. And of course, the global sections are always non-zero. You don't have to worry about this. If you look at the open orbit, then we get the connection on C star. And if you write this down in local coordinates, so remember that there is a twist involved, then this D module reduces if the monodromy around these points is trivial. Then we can take regular section. If not, then our D module is irreducible. So, I mean, one accident is that if you do the calculation that the monodromy around this point gives the same condition as monodromy over this point. And this is the reason why that when you, as you have seen from the calculations in the SL2 lectures, that when principal series break down, then there are both discrete series lying here. But if you go to higher cover of SL2, then you see that this falls apart. There you will get reducibility around one point, but not around the other point, and the symmetry is broken. So this is another interesting exercise to do. And on the open board orbit, there are 2 connections. One connection is all the structure sheaf of the open orbit. The other one corresponds to the twofold cover. So this is the one when the action of the stabilizer is non-trivial. And the standard modules are just sheaf theoretic direct images. And again, as I said, they will be reducible when we have integrality condition, where the sections can extend over these 2 points. When the sections extend over these 2 points, what do we get? We get that this LQ tau is, in this case, sheaf of sections of the line bundle in what was discussed in the Borel-Weil theory. So we get the finite dimensional representation, which corresponds to our LQ tau. And again, in SL2 lectures, you have seen that the principal series under integrality condition contained for certain parameter lambda satisfying negativity or positivity condition, I forgot how the parameters were chosen, contain finite dimensional representation as a sub-representation, and the quotient are these 2 discrete series. And this is exactly what the geometry tells us, because we take a line bundle in this direct image, and the direct image we allow sections to go on with these 2 points, and when we take the quotient, we get the Laurent series of these sections with blow up, and there are exactly D modules attached to these points, irreducible D modules attached to these points. And this is the picture in general. The problem, so now we have the classification. So what is the problem? That we have no clue in general how, say, if lambda is antidominant, how global sections of these gamma, LQ, tau look like, and these are reducible Harish-Chandra modules. In our paper with, say, Hecht, Schmidt, and Wolf, we find that necessary and sufficient condition in anti-dominant situation, global sections vanish. So we know which modules give us irreducible Harish-Chandra modules, but this doesn't relate yet with classification we discussed in the other cases. For example, since I'm behind and I have just slightly over 5 minutes, let me discuss one special case, and I will try tomorrow to give some hints how this is proved and how you get more general result. So let me discuss, for example, what is the situation in discrete series, because this was mentioned in Arden's lecture.
So, I mean, for the anti-dominant particular case, if they don't read the details, there are some.
Oh yeah, you use it, but you don't know which D module, which representation this is. So you know, you can write down in SL2, we can do silly calculations on these D modules and figure out what they are. But what is this in general? We have to have some general strategy. And the general strategy I will try to explain tomorrow is related to the other topics of Harish-Chandra work, and this is asymptotic behavior of matrix coefficients. And there is some kind of philosophical principle, and I'll try to explain why it works, that smaller support implies that asymptotics is better. For example, these two points correspond to discrete series, and discrete series have square integrable matrix coefficients. The representations corresponding to the open orbit are not square integrable. So this is simple. So if we make this observation into a theorem, then we can prove the following. Let's assume I want to describe a discrete series. Discrete series is a square integral. And as it was implicit or probably even explicit in Harish-Chandra's work, this implies that matrix coefficients satisfy certain growth condition at infinity. So, on the other hand, this growth condition can be interpreted in terms of an homology, which are geometric fibers of localizations. So for example, if we put this information together, in the way I will try to sketch tomorrow, we observe the following: that square integrable representations exist if the rank of, say, G is the same as the rank of K. Of course, this is each other condition. If this is not the case, there is not enough room to get square integrable matrix coefficients, as you will see. But under this condition, there is one-to-one correspondence between closed orbits and discrete series. For given one. I mean, I'm a little bit vague here. I mean, this is precise for linear groups, but the theorem holds in general. So basically, the discrete series are enumerated by a closed orbit. Here you have two of them. In general, you can also say precisely how many of them exist, and this gives you the number of irreducible, the number of discrete series. Why? Because for a closed orbit, there is nothing in the boundary. So in this case of the closed orbit, LQ tau is the same as IQ tau. So our representation is global sections of the standard Harish-Chandra sheet, which is quite simple. This is one observation. The second observation, and this is what is great in D-module approach, that you get exhaustion for free because you have equivalence of categories. So you know, for example, in Parthasarathy's talks, you saw that Harish-Chandra worked very hard to prove that these eigendistributions exist. Here we know there are characters of those representations, they're linearly independent, and we can, from his work on matching condition, we can show that they're uniquely determined by the values of a compact Cartan, and using Osborne conjecture, we can calculate restriction of the characters on a compact Cartan, and putting this all together, we get this another proof of Harish-Chandra's classification. And I mean, of course, the most amazing result, I don't think nobody ever managed to simplify really, is the regularity of eigendistributions. And so knowing that the characters are functions, we always have to use this fact if we want to relate, say, D-module approach to his approach. I think my time is up, and I should